All right, welcome back. Today we'll talk about some important distributions. In the last lecture, we looked at some introduction to or review of probability methods. We looked at mean variance. We looked at some of the important formulas there. Let's start today with some important distributions, and I've divided this into two halves: discrete probability distributions and continuous probability distributions. Although we have many more distribution functions, and but we don't really talk about all of them because they're not directly useful here. Even in this case, we'll talk about the first four, which are useful, and then in terms of continuous probability distributions, we'll just talk about the normal distribution. All right, so let's get started. The first and the very simplest distribution is a Bernoulli distribution. Think about any event where outcome is binary. That's a Bernoulli random variable. Think about tossing a coin, playing a slot machine, outcome of the game. All of these cases, the possibilities is either win or lose, heads or tails, 0 or 1, things like that, right? So let's define P as the probability of success in a single trial, right? So probability X is equal to Xi. I'm saying X is my Bernoulli random variable. And then X is equal to little xi. This is equal to just P if outcome is a success. This is equal to 1 minus P if the outcome is a failure. That's a Bernoulli random variable. Now, in most cases, think about it. If you go and play a slot machine at a casino or maybe at your local arcade store, you don't play the slot machine just once, do you? You don't. You play the slot machine, until you break the slot machine, or I don't know, but you don't play it just for once. You play it usually more than once. Think about uh, your favorite team you're watching playing. They're playing in a season. They don't play a single isolated game. They play in a season, right? So we usually have more than one event involved. We usually have, let's think about it this way. If your favorite team is playing in a season has 70 games, then you're probably interested in the probability of your team winning 50 or more games, or 50 games, or 60 games. When you're playing a slot machine, let's say you have money for playing the slot machine 100 times, then you're interested in how many times am I going to win the slot machine, right? That's the probability we're talking about here. So this leads us to the second distribution. Let's define this first. Okay, if we have n independent events, and or events or trials, let's put it trials. I like the word trials. Independent trials, and P is the probability of success. Probability of success in a single trial, then the number of successes, let's call it X, follows a binomial distribution. Binomial distribution. Right? And then we can say that X is a binomial random variable. Okay. All right, great. So let's define binomial random variable. Again, we are interested in x taking a little value, taking the value little x. This is equal to n choose x, p raised to the power x, 1 minus p raised to the power n minus x. Okay, and x is the number of successes, right? So it can be 0, 1, 2, all the way up to n. And then p is always between 0 and 1. This n choose x, if you're not familiar with this is basically n factorial divided by x factorial times n minus x factorial. And really, if there's a problem based on binomial random variable binomial distribution, you don't really have to use this formula. You can use your calculator and just do as simple as binom PDF, and you can come with arguments np comma x here. You're totally fine to use this formula on your calculator, completely fine. Right, so this is we just looked at probability density function, probability mass function. Now we look at cumulative probability. Cumulative probability. And in this case, we are interested in probability that x is less than equal to a. And really, you can find this out by just taking a summation of all the probabilities for all the possibilities. So x can go from 0 to a, and then you take a sum over this and choose x, p raised to the power x, 1 minus p raised to the power n minus x. And on your calculator, you can do binom CDF n comma p comma a. Right, a couple of more things here. I would like to say expectation of x, where x is a binomial random variable. This is equal to np, and then variance of x, this is equal to np times 1 minus p. Right. Okay. Let's do a very quick example here, which I like to do all the time. But let me create some space here. Let's do one example here. Let's say your favorite team is going to be playing a season with 70 games. Let's say probability of success in one game is 0.8, of course, because it's your favorite team. And then the probability, and then we're interested in probability of winning 50 games. This, this is just probability x equals to 50, and you can do a binom PDF. If you have calculators right now, I would like you to actually use the calculator and compute the final answer, which is arguments should be n is 70, p is 0.8, and x is 50. You should get an answer of 0.024. And then we can also think about probability of winning at least 50 games. And then this is equal to probability x is at least is greater than equal to 50, right? Now, we don't have a formula that can give us greater than equal to 50. So I'm going to write this equivalently 1 minus probability x less than 50. Right? Again, we don't have a formula for less than 50, but all we know is that less than 50 is same as less than equal to 49, because x can only take discrete possibilities. So this is equivalent to x less than equal to 49. And then just do a binom CDF here, you should get 0.9697. All right. All right, and then we can also think about binomial in the context of quality control. Think about a population, think about a manufacturing process. A manufacturing process is usually a very large population, right? And then in this large population, let's say we know the percent of defective parts produced is P, right? So P is the probability of success here. Success is getting a defective part, right? Doesn't matter how we define P. So for a randomly sampled, for a random sample, let's make it random sample of n items, the number of defective parts X. Now you know that this would follow a binomial distribution. Right? So I can say here X follows a binomial with parameters n comma p comma x. Okay, fantastic. Now let's do a slightly bit complicated problem here, and let's try to solve this. Let's say a firm claims that 99% of their products meet specifications. To support this claim, an inspector draws a random sample of 20 items and ships the lot if the entire sample is in conformance. Okay, find the probability of committing the following errors. The first one is refusing to ship a lot even though 99% of the items are in conformance. Now, the question is calling this as an error. And to understand this, I want you to take a step back and think about it slightly different. If 99% of the items are good, then you would technically want to say that this is a good batch, right? I would usually want to ship this batch. Now, if 99% of your items are in conformance, there's a very, very high probability that if you take a random sample of 20 items, all 20 are in conformance. There's a very high possibility. Think about having 100 items and then finding 100 items out of which only one is defective, right? So if only one is defective, if you randomly sample 20, there's a very high likelihood that all of them would be in conformance. But there's still a little bit of chance that it may not be conforming, right? And by chance, if it is not conforming, the inspector is going to reject the sample, even though the sample is very good. And that's why we are calling it error. And in future chapters, you'll see that there's a specific name to it. We call it type 1 error, right? So let's not get lost in type 1, type 2 errors right now, but let's try to just focus on the problem. When we go in chapter number 3 and 4, we'll return back and talk about this. So probability of refusing to ship the lot, this is equal to probability of one or more defective, or I'm saying defective is something which is not conforming, defective items. Can I say that this is equal to 1 minus probability none are defective? Right? Saying one or more defective is equivalent of saying none are defective. Or you can also say that this is equal to probability all are conforming, all parts are conforming, right? So we know this is, we know the probability of conforming P, this is equal to 0.99, and then you have a total of n equals to 20 samples. So now I can compute this probability. This thing right here is equal to 1 minus binom PDF, n is equal to 20, p is equal to 0.99, and since all of them are conforming, your little x is equal to 20. That's equal to 0.182. Now you see, this is not a huge probability. This is a small probability. So it says, let me, if I have to write this down and phrase it up, I would say, even when 99% of the parts are conforming, or meet specifications, there is still 18.2% probability, or 0.182 probability that the inspector will not ship the lot. Right? And that's what we usually refer to as type 1 error. And again, we'll return and talk about this more extensively in chapter number 3. Okay, let's do the second question. The second question is, now consider that only 95% of the items are confirming. Okay, less number of items are confirming now. Find the probability of still shipping the lot. You see now your lot has more defectives, right? And we're interested in the probability of still shipping the lot. What it basically says is that even though you have lots of defectives in your lot, or relatively more defectives in your lot, there is still some possibility that if you randomly sample 20 of those, all 20 are going to be confirming, and then the inspector is going to ship the lot. So we're interested in that probability. Okay, so in this case, in B, probability of shipping the lot, this is equal to probability all are confirming. In this case, your N is still 20, but your P has changed to 0.95, and your X is still 20. And if you do binom PDF, you will get 0.358. Okay, and now I would like to again phrase this up just like I phrased the previous question. I would say, even when only 95% of the items even when only 95% of the items are confirming, there is still .358 or 35.8% probability that the lot will be shipped. Lot will be shipped. So that's what we typically call as type 2 error. Right? Okay. Now there's one tiny little concept in binomial, and before we move forward, this concept is about sample fraction non-conforming. So far, let's think about X as, so based on so far what we have studied, let's think about X as the number of defective items, and then X follows a binomial N comma P, right? Okay, so N is your number of, so N is the total number of items in the sample. P is, in this case, is the probability of defective, right? And so X represents the number of defective items. Now, P is also called, there's another term for that, that's called population fraction non-conforming. That's what typically call it. Now, typically this P is given to you, right? Now, if this P is not given to you, many a times we actually estimate P. And when we estimate P, we denote it as P hat, right? So this hat notation, let me mark it up. This hat notation is basically saying estimate, right? You estimate P from data, and then P is equal to X over N, right? Now, if you look at P hat is a random variable X divided by a constant n. So p hat is still, even though it's an estimate of p, it is still a random variable, right? And if it is still a random variable, we are sometimes interested in the probability of p hat. So what I mean by probability of p hat is basically saying that p hat is probability that p hat is less than equal to some number a, right? And if I have to compute this, I would write this as probability. P hat is just x over n. This is less than equal to a. This is equal to probability x less than equal to an. Now here it's a little bit, the trick, that the issue here is, the problem here is a times n could be a decimal, right? But x cannot be a decimal because x is the number of defective items. So what we do here is we basically do an adjustment by taking a floor of an, right? So floor is basically saying that if you have a number 50.5, floor will give you 50. If you have a number 50.9, the floor will also give you 50, right? So floor is the largest integer less than the argument. Argument in this case is an. Does that make sense? Okay. All right. And now you can just do binom CDF. You can just do binom CDF n comma p comma an. And then I have a problem based on this. So let's do this as well. A random sample of 100 items is drawn from a production process every half hour. The fraction non-conforming of the process is known to be 0.03. So the fraction non-conforming, it says fraction non-conforming, right? So sometimes if it says fraction non-conforming, it is same as population fraction non-conforming, right? So I'm going to say p is equal to 0.03. What is the probability that the sample fraction non-conforming is less than 0.04? So it is asking us to compute probability p hat is less than equal to 0.04. Right? And I can use the same formula that I just did. This is equal to probability x less than equal to floor of a times n. What is a in this case? A is just 0.04 times n is 100. This is equal to probability x less than equal to, this is coincidence that it turns out to be an integer. It doesn't always have to be. And now you can do here binom CDF 100 comma p is 0.03 and x is 4, and this should give you 0.818. And then we have second question. It's a very similar problem. In this case, you're interested in probability p hat is less than 0.04 greater than equal to 0.02, right? And then this is equal to, we just do the same thing here, but I would first write this as probability p hat is less than equal to 0.04 minus probability p hat is less than 0.02, right? Or you can actually do it slightly differently. Let's do it slightly differently. Let's first convert this into integers, then it will make more sense. Let's say this is equal to probability p hat. I can replace it with uppercase x, yes, divided by n less than equal to 0.04 greater than equal to 0.02. This is equal to probability x is less than equal to floor of 4 greater than equal to floor of 2. You multiply n both the sides, and then this gives you probability x is less than equal to 4 greater than equal to 2, right? And this is nothing but probability x is equal to 4 plus probability x equals to 3 plus probability x equals to 2, right? You can also write this if you want to. You can also write this as probability of x less than equal to 4 minus probability of x less than 2, right? And then you do binom CDF in the first case. In the second case, also you'll have to do binom CDF. One thing that you have to be very careful is, again, since we have less than 2, I will have to rewrite this as probability x less than equal to 4 minus probability x less than equal to 1, right? Because less than 2 is basically less than equal to 1. And if you compute this, you will get 0.6232. Okay, fantastic. All right, so let's do let's also finish up hypergeometric distribution, and then we'll stop this lecture. I don't want to make lectures more than 30 minutes, so yeah, let's actually stop here, and then we'll come back and discuss hypergeometric distribution in the next lecture. All right, thank you.